Welcome back to Polly's Introduction to Computer Networks. And hi, Jeremy. Okay, so, hey, guess what? Oh, hi, Tingyi. Hi, Jiabao. Hi, Elu. All right, you know what? Today is week 7, ep11. That means we are starting the second third of the semester. If you recall, the first week of the lectures, Polly was describing the semester is divided into 3 parts, okay? And each part ends with an exam. So we just completed the first third, all right? And you probably get a sense of how the class's pace is like, okay? And the assignments are like, and the exam is like. So let's try to enjoy the rest of the semester because usually time flies. You see, it's already a third of the semester. And yeah, hi to Yun Shao and Tao. Good, so let's, oh, one more thing. The assignments due this Saturday. What do we have? Yes, we do have PA4, that's the 4th PA. And we have 4 quizzes this week, but all 4 quizzes are straightforward. Okay, so I guess the trickiest one is PA4. Good news is that several of you guys have completed PA4. Okay, and I see that many of you have started PA4. Good for you. But it's due Saturday, and it's the second hardest assignment. Okay, so make sure that you use the time from now to Saturday and complete PA4. And the topic today. Okay, we are not yet done with chapter 2, the application layer protocols. If you recall, in the first third, we talked about the web application. We talked about email. We talked about DNS as an application layer protocol. And we also introduced a couple P2P applications and the protocols behind. Okay. Hi, Maria and Isa. Okay. Yeah, just on time, just in time. And here today, there's one more application. It's the last application, but not the least. Okay, it's called the multimedia application, aka the applications that we send videos or receive videos. Okay, so in this first video, Polly is gonna tell you how important video content is and how much of these video content is being sent over the internet today. So it's, you know, the last but not the least important application. And then Polly will also talk about the challenges of delivering these videos over the internet. So this video, 4.5 minutes. 2.6, video streaming and CDNs. Video streaming, the term is very simple. Okay, YouTube, Netflix, Hulu, and Kankan, they're all video streaming services. So what they do is essentially stream videos to you. Now, what is less heard of is this term, CDNs, Content Distribution Networks. You probably heard me talking about these networks a little bit when I was talking about the internet structure. All right, so there's backbone of the internet, there's ISP, and there's, you know, end users. But there's also these global service providers. Content distribution network is one of these global service providers, such as Google. Right? So one of the oldest CDN company is called the Akamai. Nowadays, we do have these cloud service providers, Azure, AWS, okay, also in the market for competition to provide content distribution network services. So in a way, the video streaming services such as YouTube is actually the subscriber of the CDN services. So video streaming services high up, very close to the user, and indirect interaction with the user. The CDN is one, you know, half layer below, although still in the application layer, but half layer below, right underneath the video streaming services. Now, in order to explain why video streaming services these days uses CDNs, I'll have to share first how hard it is to provide video streaming services. Let's look at the video traffic coming out of major services such as Netflix and YouTube. So this is according to US residential ISPs statistics. 70% of the traffic coming downlink to the household from Netflix, 60% from YouTube, So just these two video services together is already more than 50% of the downlink traffic. So you see, video, a major consumer of the internet bandwidth. And this is mainly because of the number of users we have on each of these video services and the demand. Okay, so the number is still growing, demand is also rising. So we see challenges ahead. And the first major challenge is the scale. So that is related to the demand. As the number of users increase and as the number of video demands increase. So when we have users at that scale, can you imagine serving all the videos using just one single server? If you recall, when we were talking about the hierarchy in DNS, the domain name system, we are only serving what? Host to IP mapping. That is actually very, very short messages. But now we're serving videos. Even serving short messages like what DNS is doing, we need a what? A distributed system. So you can imagine that a single mega video is not going to work. The second issue is also this. Hey, because we have so many users, and these users could be like Polly sitting right here using a desktop and connected to the wired network. But it could be, some of you guys out there, still taking the metro. You might be connected to the internet using 4G and you are moving around. So the connectivity and the internet access, you can imagine, me and a metro commuter will be very different. You cannot be sending a high quality video stream to such a user on metro and moving around. But hey, send me, I can actually take high quality video, but send me a low quality video. Neither of us will be happy. All right, so we do have this other challenge here. Heterogeneity. Different users will actually demand different qualities because we have different capabilities. Some of us are stationary, some of us are mobile. Some of us has a lot of bandwidth to download videos, but some of us don't. Right? So to address the demand, to address the heterogeneity, okay, in these users, solution is to use CDN, which is a distributed application level infrastructure. We'll definitely talk about CDN more later. Yeah, so keep in mind this term, CDN. Okay, so there's a distributed network of servers, just like what? DNS, but the architecture is quite different. Okay, now before we talk about transmitting videos, the mechanisms we use to transmit the videos, Holly would like to talk about video a little bit more because video is what you see, okay, and there's also a time. So there's a space and time notion. Okay, so it's a two-dimensional analog signal in a way. So this analog signal, before we can transmit, we need to convert it to digital form so we can first save the video. Okay, so that process of converting from the analog signal to video to digital is called encoding, video encoding, and the mechanism used to do the encoding are called the video codecs. Okay, so in this coming video, we'll talk about the nature of the videos and how we exploit properties in this analog signal so we could compress the video in the process of doing digitalization. And the smaller we can keep the video files as small, the less bandwidth requirements it is to send these video files. Okay, so this video a little bit long, but it talks about the fundamentals of digital videos that we are about to send using the internet. Now let's talk about the video a little bit more. This is the content we are distributing there. Originally, it was an analog signal. It's a sequence of images that we are displaying. Okay? And the display is at a constant rate. That means at every time unit, you take a snapshot of what it looks like right now. Okay? So therefore, at a constant rate, a sequences of these images. So for example, we take 24 images per second. So that is what the cameras are doing, taking images continuously. Right? So Poly right now is sending 30 images per second, or sometimes it's also called 30 frames per second. Your display, okay, will be displaying 30 images per second as well. Now, 30 images per second is actually pretty low. Therefore, from time to time, you see poly selection is a little bit, awkward, not exactly smooth. These days, in order to make sure that you have very, very smooth motion, 60 frames per second is the way to go. Right? But hey, sending 60 images per second versus 30 images per second, that is at least twice the amount of traffic. So you see a little bit of trade-off there. If we want very high video quality, that also usually imply higher bandwidth requirement. And the digitalization process is this. So every second we take a certain number of images, and within each image, we divide the image into discrete number of these pixels. So you see each of these red dots is a pixel. Okay? And for each pixel, we use a limited number of bits to represent the color. Okay? So usually the intensity of the red color, intensity of the blue component, intensity of the green component. Now, because the number of bits is limited, so that you actually approximate the actual intensity to some quantile. So this is also called the quantization process, digitalization or quantization process. Now, coding. So provided all these bits being generated, the next thing we do is to just simply send it. Okay, how about that? Well, that was actually what we were doing maybe a couple decades ago. But nowadays, we add compression mechanisms or coding mechanisms. All right. So compression, coding. Compression is more specific, meant that we would reduce the number of bits we need to transmit, reduce the number of bits we need to store for the same content. But coding usually is more general, not necessarily reducing the size, sometimes increasing the size for the purpose of trying to recover from errors. So coding is a little bit more general. It's just that when we're talking about coding videos, it's usually just compressing videos. And we're exploiting redundancy that is natural in the content. So redundancy could exist here, within one frame, within one image. You see here, the sky, all these pixels in the sky, they would actually look very much the same. The colors are pretty much the same, right? So that is called a spatial coding. So instead of sending all the values one by one, how about sending only two values? The color and the number of times the pixel, the color is going to repeat. So two numbers instead of n numbers. That reduces the number of bits we need to transmit. The other way, so that was spatial. The other way is temporal. So that is to look at this from one frame to another frame when we're in action. For most cases, slow action, you will see that frame I and the next one, I+1, there's not going to be much difference. So, hey, these pixels remain similar here. The colors pretty much stay the same, right? So why don't we, instead of sending all the pixels in a frame, send only the differences from the new frame to the old frame, right? So if we take a subtraction, newer frame subtracting the older frame, then you get very little differences. Most of the pixel differences are probably just zero. Then it's much easier to send a whole bunch of zeros, which you could use just zero and the number of times the zero repeated itself. So a combination of spatial and temporal redundancy exploitations. And the coding schemes, the really, really old one, those that are decades ago, are the constant bitrate coding. Because what? The number of bits is fixed to represent each pixel, and the number of pixels is fixed per image, and the number of images you take per second is also fixed. Therefore, the number of bits you're sending out is also fixed. Nowadays, the coding is variable bitrate. So it really depends on the amount of spatial and temporal redundancy you can exploit. Those movies with really, really fast actions, then you don't get very good compression rate because the from frame I and frame I+1 usually large, so you don't get to save too much. As a result, the bit stream you send out is in different bit rate. So lots of actions, high bit rate. Not much motion, low bit rate. So examples, this is MPEG version 1, MPEG version 2, MPEG version 4. And you see in the older version, the encoding rate is much higher. Nowadays, using MPEG 4, the suffix of the file names of MPEG-4 video is usually just this, MP4, something something.mp4. Compression rate is really, really good, so we could send very high quality video under 1 megabits per second. Now, yeah, you see version 2 seems to be requiring more bandwidth. That's because it's in DVD quality. The number of pixels that you're sampling is way higher. Okay, so CD-ROM is actually pretty old, as I said, a decade ago, and maybe a couple decades ago. All right, now next, let's talk about transmitting these videos. All right, in this coming video, at the very beginning, Polly will actually explain transmitting file. Okay, because a video file is content that has some time dependency. So it's not exactly like the regular file transfer. Instead, when people say when uploading or transmitting a video, we actually say we are streaming a video. It's continuously downloading, okay, parts of the video file. Okay, so this video, a little bit long, okay, about 5 minutes. Streaming stored video. This is among the most used video streaming services in the world right now. So there's live video. There's also interactive video. Those are actually harder to do. We're not going to talk about those services. If you're curious, please feel free to dig into Chapter 7 in the textbook. But as an introduction in Chapter 2, we just talk about this one here, the stored video. This is also the video on-demand service that Polly mentioned slightly earlier. The service model, hey, surprise, surprise, client-server based. So the server being where the videos are stored, okay, and the client is the consumer of the video. Okay, quite straightforward. And streaming is just to pull the video frames one by one across time. And the first protocol that I'll be introducing is called the DASH, Dynamic Adaptive Streaming over HTTP. So from here, you see that this is what video streaming over HTTP and over, therefore, TCP. So unlike what we have expected probably, right? Video services does have high bandwidth requirement and short delay requirement, but TCP, how would it serve? Okay, well, for video streaming services. Well, the main reason will be explained the next topic called CDN. Here, what we are addressing is this. Between the client and the server, there's the internet. Okay, internet fluctuates a lot if you think about it, right? People come and go, sending other video traffic, sending other big file download traffic. Now these is gonna, interact with each other, and therefore the available bandwidth really between the client and the server is varying a lot over time. So Dash here is to try to adapt, okay, to the internet conditions. That is very dynamic. All right. So the main intelligence is actually at the client side. Okay. What server did is just to prepare such that the client can be intelligent about, okay, about streaming video over the internet. So what the server is preparing is doing this. Video files are usually large, and it's usually many frames being played or being transmitted over time. And so what the server did first is to divide the video files into shorter segments. Okay. So here in the site, we call it chunks, video chunks. A little bit like in P2P, BitTorrent actually cut big files into chunks. And each chunk is stored and encoded in different rates. If you recall when we were talking about videos, right? Depending on how much detail you want to keep in the video, depending on the quality of the video you want to be able to play back, you might want to encode it at different rates. Okay? Higher rate usually meant that more detail, better quality. Lower rate usually meant less detail, lower quality. But the trade-off is, hey, for high quality video, you do need a bit more network bandwidth to transmit. But for lower rate video streams, there's less need of bandwidth. Okay, chances higher that you don't run into trouble sending a low rate video stream over the internet, right? So, well, to allow these, flexibility, okay, depending on how the client senses what the current network bandwidth is, the server is actually storing each chunk and encoding multiple versions of these chunks at different rates. So when the quality, when the network bandwidth is good, then we could download a higher quality video, a higher rate video. When the network bandwidth is not sufficient, we'll have to drop to a lower rate, okay, version of a chunk. Now,
What's being communicated to the client from the server is this, the manifest file, which is providing the location, the address of all these different chunks at different rates. All right. Now, the client. What the client does is periodically measure the client to server or server to client bandwidth. Okay, so what it means here is exactly the available bandwidth. Right. And then, provided this bandwidth limit, consult with the manifest file and then request the chunk, okay, the client is looking for at the time, and chooses the maximum rate such that it's under the bandwidth limit. Okay, so measure periodically the available bandwidth, pick the version of the chunk such that the rate is right below the limit. Okay. And at different point in time, so periodically, the client does the measurement of the available bandwidth. If it gets back up again, then you pick a rate that's a little bit better. Okay. Otherwise, if the available bandwidth drops, pick the rate that is a little bit lower. Right? So you choose different coding rate depending on what the available bandwidth is at a given point in time. Right?
All right, so that's how dash work. And before we go to quiz 15, let me answer Justin's question here. Okay, so we talked about how video is encoded. What about audio? Okay, do you use the nature of the audio signal being a sine wave? Yes, we do. Yeah, we actually do both. We do frequency decomposition of the audio and then remove the components that are not audible to human beings, because these audio files usually serve the purpose of human listeners. But after that, we kind of sample the original analog signal and quantize, okay, the value in the analog signal and convert it to digital this way. And we also use some coding schemes to try to exploit certain level of redundancy in the audio. Okay, so audio encoding and video encoding quite different. And in fact, when we are sending video, yeah, the audio track and the video tracks are, being sent at the same time. Okay, so it was actually a little bit challenging synchronizing the videos and audio tracks at the receiver end. Right? Very good question, Justin. And hey guys, quiz 15 is coming. Okay. Yeah, so this is asking, in case you are now a dash client, okay, and this application is using H.264 video codec. Okay, and the nature of H.264 is this: if you want to send a 4K video, usually the video streams coming out is at this bit rate, 16 megabits per second. 2K video, you see a lower resolution than the bit rate. Okay, the bandwidth requirement therefore is lower. Okay, and you see so on so forth. At the lowest resolution, 360p, the bit rate at maximum is 800 kilobits per second. Okay, so now you being the dash client, can you tell me which resolution video you would download in case the available bandwidth is 51.3 megabits per second? And which resolution in case you find the available bandwidth downstream is only 2.5 megabits per second? All right, let's go to the discourse space. Guys, go to the W7 quiz 15 channel. Okay. Yeah, as I said, the quizzes this week is quite straightforward, because as we enter 2.6 and chapter 3, much of the contents are very technical. Okay, those students who are good at math and physics usually have no trouble. Okay, and these quizzes will be straightforward for you guys. Yeah, exactly. If the available bandwidth is 51.3 megabits per second, we could accommodate 4K. If it's only 2.1 megabits per second, we couldn't take 720p stream. So 480 is the maximum, is the best. Good. So you get the idea of dash. So you keep measuring the available downstream bandwidth, and you request the video that is the best quality, but within that available bandwidth limit. Okay, great. Yeah, I have to say that for this quiz, we'll take the fast solvers, okay, for bonus. Good, thank you. And now we come back, okay, talking about transmitting video. So what Dash does is to tell the client which resolution, which copy, which encoded version of the video to download. But earlier you heard that we have the CDN thing, right? It's a network of servers, meaning these videos are stored on multiple servers. So there are still many issues yet to be determined, or things to be determined by a client. So once we know what is the best resolution, but from which server, right? There's a network of servers. So where it is, this video is going to tell us more where and when to download these videos. And in the when part, it's not just when to start downloading, but also about when to pause downloading and resume downloading. Because it's a little bit tricky because the bandwidth there, okay, on the internet fluctuates. Okay, a lot of times they are abundant, but at some point in time there could be significant congestion and the available bandwidth suddenly drop. Okay, so you cannot just be streaming the videos in a constant pace, because you are going to exhaust this buffer space before your video player. Okay, because these videos we continuously fetch from the server will enter the buffer space first. From the buffer space, your video players on a very constant speed extracting the video frames out. Okay, so these next two videos are very important. First one, let's talk about where a client will try to download the video.
So you heard that the client is actually pretty busy. It's measuring the available bandwidth and deciding what is the best rate of the chunk to download. So bandwidth, higher rate, or lower rate. So this is one of the intelligence the Dash client exercises. There are actually two more intelligences that are implemented in the client. The second one is this, where to request the chunk. And the third, when to request the chunk. Let's talk about each of these a bit further next. Where to request the chunk. What happened there is that in the manifest, there could be multiple URLs indicating that there are multiple servers carrying that particular chunk at that particular rate the client is looking for. Now, among many of these physical servers offering the same chunk, same rate, the client needs to pick one of these. Okay, so the typical decision is to pick the server that is the closest to the client. By closest, usually people mean the server that is showing the smallest delay back to the client. Now, how do you get the delay from the client to the server and back? Well, the client can send a short ping message, okay, and see how long does it take for the server to answer back, or to send trace route, for example. So clients are also, in the meantime, sending these probes to find out which of these servers will be closer to the client. And this is also done periodically, just like how the network bandwidth is measured.
All right, okay, so we had some other questions. So Mikhail was asking, can Dash facilitate smooth playback for real-time video streaming under challenging network conditions? And Elu is trying to answer the question. That's great. You know what? It's good and yes and no. Okay. Yes, in a way that Elu was right when there's congestion, right? Available bandwidth suddenly drop. Yes, you try to download a video with lower resolution because you find the available bandwidth is lower, and therefore you download a video with lower resolution. But it's not just like that, okay? Network is not the only reason that you need to adjust the speed that you download or stream, okay? The player there, okay, the video player there running on your computer could suddenly be busy because there's a congestion on the player end. Then that buffer there will stack up. Okay, in that case, you want to also inform the server to, you want to fetch the video from the server slower to avoid buffer overflow. So this coming video to ensure smooth playing of the video or management of the buffer. Okay. Timing. of controlling the video streams.
When to request the chunk. This is actually the intelligence that is a little bit hard to explain because we did not talk about a very special component in a streaming system. So let's go back a little bit to the architecture. So there's the client side and the server side. At the server here, we have huge hard disks storing video chunks and allowing clients worldwide to pull the video streams down to the internet. First component these video frames hit is the socket, okay, at the client. But then quickly, it enters this thing called the video buffer, okay, or the client-side buffer. So video frames we're getting here first. So the app that the users are playing with is more graphical, okay, and where you see a play button like this, okay, when we hit play, what happened there is that the client sends a short message to the server that, hey, I'm gonna download this video at this rate, okay, and video frames begin flowing in. All right, so you can think of the buffer like a bucket, and if you think of these video frames as a flow of water, then it will be easier to understand. Right? So usually what happened is here, the client, before we really play back the videos, we keep a number of these frames first. Okay, when there's enough of these, so it's like a reservoir here, the buffer. Okay. Then we begin to pull the frames one by one and then render it on the player. Okay, so the time you hit the play button until the time the first frame begins playing, that is called the buffering delay, okay, or the startup delay of these stored video streaming services. All right. Now, the reason that we actually store a number of these frames before playing back is exactly because of this. Usually the playback rate is constant. So for example, 60 frames per second. So this is usually to ensure a smooth experience. Right? So viewers will all prefer a higher frame rate if possible. Okay. Now let's say that, hey, we're going for 60 frames per second rate, but the network bandwidth here suddenly goes really bad. Okay. What's occurring here at the buffer space is this. Well, we're fetching still 1 frame per second. Okay, 60 frames per second. That is, oops, sorry. So 1 frame per 1/60th of a second. But the thing is that the network bandwidth goes down. The incoming rate of the frames will be much lower, and it will not take much time until what? We see the buffer space emptied up real quick, and eventually there's no more frame in the buffer. Okay, that is called the buffer starvation. The buffer is starving of the video frames. Is that good? It's actually not good. What happens here is you're seeing your screen smoothly playing video frames one by one, but suddenly what? It freezes. Okay, so that is called an interruption. So that's very disturbing to the viewing experience. Not good. So the client usually sends back another message to the server saying that, hey, you know what? The network situation is not good. How about that I download another version of the video such that the rate is lower? Okay, I'm okay with the lower quality because otherwise I will not be able to sustain the frame rate I was looking for. Okay, so usually you'll be automatically switched down to a lower resolution, okay, or a lower frame rate, for example, just to ensure smooth playing back of the video frames. Okay, so when to request chunks so that the buffer starvation does not occur. Right? And let me make sure this is clear. Right? So that message from the client to the server asking video chunks being sent with a lower rate version, that should occur before actual starvation occurred. Now, as to how much earlier, that is the intelligence the client needs to decide. Right? So Dash allows the client to implement different strategies to decide when to start changing the rate, okay, automatically according to the network bandwidth to avoid buffer starvation. Now the other situation is this. The client also needs to decide when to send back a message to the server such that the buffer does not overflow. So this is the other way around when the incoming rate here is really nice. But the server here, the client over here, the user over here, the client is what? Hitting a pause button, for example. taking a restroom break. When this happens, right, the player will not be fetching frames one by one as usual. And quickly what? Hey, the buffer space is also limited. We have a buffer overflow situation. All the subsequent frames coming in here will get what? Dropped. So this is just like in the router. We have the buffer space for the packets. Now, in case the outgoing rate is too slow and incoming rate is too high, we have what? Packet drops. Similarly, if the user is hitting pause or doing something else, then we might have a buffer overflow situation. This is not good either. We definitely do not want to miss frames in the middle of video playback. So clients, therefore, send back a message to the server, asking the server to hold. Okay, now stop sending the frames until I tell you so next. So this is also another intelligence the client side implements, telling back the server now to stop and hold the sending of the frames.
All right, so sending video, streaming video, it's a very interesting topic. There are two more questions. So Justin was asking whether it's possible to stream through a P2P network. In fact, there were quite a few P2P applications for video streaming. Something like PP Live, PP Stream. Yeah, there are many of these. Okay, and there are also streaming videos that have copyright issues. So those are VOD, video on demand, which means it's not live video. Okay, so you can imagine, Justin, using a larger buffer space, or if the viewers don't mind waiting longer time until there is a user holding a particular chunk to arrive. Okay, so the viewing experience is much less pleasant as the dedicated server client-based video streaming applications. So Netflix a lot more reliable, YouTube a lot more reliable. PP Live, PP Stream, it happens very often that in the middle of watching a video, the screen is frozen because there's a chunk that's missing, okay? And your client or your peer has trouble downloading it. For live video, I would say P2P architecture very much not gonna work. Okay. But hey, for short video calls, it might work, such as Skype. Or short video conferences, it might work. Elu, hey, how do you determine the size of the buffer? That's a $1 million question. Usually it has something to do with the transmission rate and the delay from the client, the server to the client. So you want to keep you want to keep like a round trip amount of data in the buffer. Okay, but that's the basic size. Okay, if one wants to buffer more to ensure really smooth playback, then one might allocate more buffer space. Okay, so usually these multimedia application developers, they will continuously trace their implementation's efficiency and see how the users behave and decide empirically what is the perfect size. Okay, too big, then you can imagine some of your users might not have high-end machine, not enough memory, okay, to store, to provide the need of the buffer. Okay, so if you want to be as accommodating to users having different devices that are less resourceful, for example, then go with this empirical approach. Okay. So I hope those addresses the questions. Next, hey, Dash is something that we run at the client side. What about the server side? We do have a CDN, right? A network of servers. Okay, how the servers interact with the clients? That's another big part of a multimedia application design. All right. So let me first, by playing this video, telling again why we need a network of video servers, and I would introduce there are two forms or two types of connecting or placing these servers on the internet. All right. So this video.
CDNs, content distribution networks. This is the part in video streaming services Polly finds the most amusing. Some of you might know, many of the global services that are popular worldwide uses some sort of CDN in the back. So that includes Gmail, Dropbox, even the Zoom teleconferencing system that is a bit controversial these days. The reason for that is this. You hear a little bit back, dash. Okay, so dash there is nice. The client can actually adapt. Given this much network resource, we ask for the video chunks and the version that's just behind, okay, just below the available bandwidth. Okay, so this adapts to fluctuations on the internet, which includes when the number of users increases, yeah, the remaining available bandwidth will be lower and lower. The dash there does is just to adapt to the change. The thing is that the change could become unbearable. So if the number of users increase continuously, okay, and if a high number of them are demanding the service simultaneously, you could end up with available bandwidth that is so low, it's not even sufficient to serve the chunk with the minimum rate. And to deal with the network capacity issue is what CDN here is mainly to address for. Again, there's a critical issue on popular systems on the internet today, the scalability issue. Okay. And CDN here magically addresses some aspects of these scalability issues. Let's step back a little bit and look at option 1. So this is to contrast CDN, and this is the simple, naive solution. What about using just one server? Yeah. If you recall when we were discussing DNS system, the name IP address mapping service, we were saying that originally there's only one server instead of having a distributed service, isn't it? Yeah, using one server, we have issue like this, single point of failure. That server down, the entire service down. The mega server down, the video streaming service is also down. And that one server there is also the point of congestion because everyone is asking for its service. And there'll be part of the world being happy because they are close to the server, but there will be the rest of the world will be unhappy because they are farther away from the server. And delay long is not good, and there's also a fairness issue, isn't it? How come you always get to enjoy short delay service, and how come, okay, I always have to wait? And last, this one is more distinctive in video streaming service. In DNS, the name to IP mapping are all short messages. But here, for video streaming, it's continuous, and each frame is already bigger than the name IP mapping. So we're sending these streams repeatedly, and some of the streams are probably the same. So users might be requesting popular videos, which means we are sending multiple copies of the same video over and over again. Right? Now, not a very thrifty way of using the network resource. Okay. Solution like this, definitely not scale. This is very clear. And that takes us to option 2, which is exactly what CDN is doing. That's, instead of using just one physical machine storing one copy of these content, that's use multiple machines storing multiple copies of these content. And more importantly, okay, distribute them around the internet, making sure that they are very widespread geographically. Okay. And the point of doing this is so that, hey, if there's a server here, the clients around it will be able to communicate and get the content within the local area. Therefore, the network capacity, other than this part, can be opened up for other clients interacting with other servers. Okay, so the number of duplicate video transmission can be reduced. A more efficient way, a more thrifty way of utilizing the network resource. Now, let's talk about the two models the CDNs are architecting their physical infrastructure. First one is called the interdeep. Okay, so this is actually speaking that the infrastructure, the machines themselves, okay, for storing these videos are actually deep, closer to the end customers, deep into the ISPs, to the local ISPs, so that they are close to the end customers. Akamai, one of the oldest companies, is implementing exactly this architecture. Therefore, there are so many locations around, okay, in Akamai. Pretty much for each local ISP, Akamai might probably set up a site where you see typically a rack of workstations, and they are redundantly connected to other machines in the access network, other routers in the access network, and potentially very close to the users. So Akamai there, when they deal with an ISP, they rent for the rack space, they rent sometimes for physical machines on the rack. They definitely subscribe to the connectivities provided by the local area access networks. Now the other model is bring home model. Okay, so by bring home, these CDN architecture is to say that the physical infrastructure, the servers, okay, they're storing video contents are actually closer to the service home, where the origin of the video sources are from. Essentially, the company generating the video. Right? So it's actually closer to the home company. Therefore, they are actually higher up in the internet hierarchy, closer to the core instead of to the local access network. Okay, so they are actually very close to these POPs, the internet exchange points. So the idea is that such a CDN company will build up a few racks of these workstations and just connect to the POPs where they get access to the rest of the internet. Right? Now, because the number of locations is very limited as number of POPs are also limited, so there are not many of these sites. And the sites tend to be bigger. Instead of calling them sites, they are called clusters. Okay, so the physical infrastructures will be formed by server clusters. Okay, few of these clusters interconnected through the POPs, the internet exchange points. So they did not go deep into the access networks. Limelight, this is a cheaper CDN service, offers bring home CDNs. Now, so you see a little bit also advantages and disadvantages of the two models. This closer to the end customer, some big wealthy service providers might subscribe to this because potentially maintaining the infrastructure is very high cost. Now, those smaller service or smaller content providers, not quite as wealthy, then might subscribe to a bring home CDN service.
All right, so the next video offers an illustration of how the server end and the client end interact. It's very important, and for the continuity's sake, please allow me to borrow 3 minutes of the off class time from you guys. Okay, so let me play this video. Now you will see how a multimedia application work.
And let me illustrate how the content consumer or the client, content provider, the origin server, as well as the CDN. Okay, CDN is the one distributing the content, how the three components interact. And I'm going to use Netflix as an example. All right. So client here will be retrieving a video, and origin server here, the content provider, Netflix over here. So CDNs, the content distribution network that Netflix subscribes to, will be allocating a number of physical machines worldwide, okay, and stores copies of the content. All right. Good. Okay, so the motion is this. Okay, a customer turned up, okay, and decided to watch Mad Men, the movie. Okay, so the user here is obviously a subscriber of Netflix, then it would send the request to Netflix. And Netflix will then send back a manifest file telling the subscriber where the copy of the video is stored. So this guy, this guy, this guy, this, all 7 of them will be reported to the client, to the subscriber. And subscriber then will pick one of them. Okay, so redirected to the nearby CDN to retrieve the content. Now what's nice about having CDN is not just the content therefore is closer to the client, it's also to address this issue. If the network goes bad here, okay, from the first CDN, the client there can choose a different CDN where the network congestion is lighter and go this way. And CDN working this way is also called a over-the-top service. Allow me to explain. And it's better explained illustrating it this way. So let's bring all these entities involved in a CDN service high up, like this. Okay, so you see there's a separation of the internet physical structure and the OTT service. So these CDN servers, as well as the original server, as well as the client, they form a network. It's a service network. It's a network formed by what? Hosts only. Now that's an abstract away the infrastructure here using just a channel. Okay, so you see here high up, this is a network. And CDN, you can think of it as a service provided to the content provider such that we enable end-to-end or host-to-host communication. So it works like there's a network at the application layer. Now, maintaining such a network such that it works very efficiently distributing content is not easy. There are a lot of key design challenges. Okay, one is, hey, as we mentioned earlier in the example, right? The client will then select a nearby CDN node to retrieve the content. Okay, that is usually because the delay will be shorter, and the segment of the internet involving the communication is short as well. Therefore, less chance of other traffic interfering with this one. But how do you know a shorter delay one is certainly the one that uses the shortest segment to travel? How? And maybe you want to use a combination of short segment and short delay. So, yeah, exactly how you design selecting of the CDN node, that selection algorithm, that is something to be investigated about. Okay. Second, in the presence of congestion, well, congestion comes in very light level, sometimes very heavy level. Would viewers be really unhappy about a certain level of congestion? It might really depend. Okay. So how do you know when to switch from one CDN node to another one? Yeah, that is another challenge. Okay. So one could come up with algorithms that switch ahead of time before it goes really bad, or switch right at the point that's needed. Okay. You see that each of these strategies may carry certain advantages and disadvantages over one another. And last, wow, at the beginning, right, we said that CDN would choose a number of physical machines and maintain duplicate copies of a certain video. But which machine? And which video? Yeah. So this really has a lot to do with resource allocation and where the demands are. You want to make sure that the content is pushed closer to the demand, but you cannot be copying all the content, right, to every CDN node. So how do you conserve? Again, challenging problem. If you're curious, definitely read more into chapter 7.
All right, so that's how multimedia applications work these days. And with that said, thank you for the many questions. And we have 3 minutes delay because of the many questions, but it's a good thing, right? So the concepts of doing multimedia streaming gets a little bit more clear. And with that said, I say goodbye. I see you tomorrow morning. Okay. Tomorrow we're going to start talking about the transport layer protocols. Okay. TCP and UDP essentially. Okay, bye, guys.